Hey everyone. In this video I'm going to talk about random variables and probability distributions, and particularly how we can characterize these probability distributions. So in the previous videos we have considered various experiments that involved kind of stochastic events, like flipping a coin that could be heads or tail, or voting decisions for one of the candidates in the last presidential election, or abstaining. And now we introduce the concept of random variables and probability distributions to basically further characterize these events mathematically. Okay. The whole idea behind random variables is that we take the events that are part of an experiment that we talked about and assign numerical values to these events, right? So a random variable is defined as assigning a numeric value to each event of the experiment. These values represent mutually exclusive and exhaustive events, together forming the entire sampling space, right? So in the context of flipping a coin, this would be, assigning a 1 for heads and a 0 for tail, for example, right? Or assigning specific numbers for vote choices, right? We can distinguish two kind of basic types of random variables. On the one hand, we have discrete random variables, which take finite or at most countably infinite number of distinct values, right? So these are discrete values. This could be counts, or as I said, the coin flip, or rolling a die and the number that is on the die, things like that. And then we have continuous random variables, that basically assumes an uncountably infinite number of values, right? So any continuous random variable, you could think of, processes that involve, I don't know, a length of time, for example, and things like that, that are ultimately continuous variables. Okay. Um, so a couple of examples here. I mentioned already the coin flip, where we assign the number 1 for a head, for the event of a head, flipping the coin, and it lands on heads, and 0 for tails. Okay, there are other examples. For example, in gambling, we could say you could win, if you gamble, you can win $100 or lose $10, right? Or you could also think of this as discrete two different events, or you could also think about this as a continuous random variable if they're, basically any value between, or any money value could, theoretically be part of that gamble, essentially. I talked about voting. If we just look at turnout, we would assign the numeric value of 1 for the event that a voter actually turned out to the polls, and 0 if not. Or a lot of the survey responses that we see in nationally representative surveys, where we have Likert scales or agreement scales between strongly agree and strongly disagree, and we can assign numeric values to each of those events, to each of those outcomes, right? And that's what we mean when we talk about a random variable. Is the variable basically the assignment of numbers to specific events that are part of an experiment? Okay. So what is then a probability distribution? The probability distribution describes the probability of an event that a random variable takes a certain value, right? So it's basically the distribution over the possible types of values that this random variable can take, right? So for example, the probability to vote is basically composed of two probabilities: the probability of vote being equal to 1 and the probability of vote being equal to 0. We could also think about conditional probabilities in this context: the probability to vote conditional on education being, for example, larger than 3 or something like that, right? So those are examples of probability distributions that basically describe the probability of an event that a random variable takes, a set of values. Okay. So when we want to characterize probability distributions, there are a couple of kind of basic characteristics that we can compare to kind of specify and ultimately describe these random events and the random variables and their underlying distributions. The first thing that we want to kind of that we always want to look at is the probability density function or the probability mass function, depending on whether this is a discrete random variable or a continuous random variable. Continuous random variables have what is called a probability density function, and discrete random variables have what is called a probability mass function. And I'm going to explain in a second what this difference ultimately means, right? Essentially, both the probability density function and the probability mass function describe how likely it is that x, some random variable, takes a particular value, okay? For a discrete random variable, we have probability density functions, and usually these are just denoted as f of x, where x is the value that is realized, or the value of the random variable that is realized, okay? So we have a function that basically describes the probability density, or how likely each of the possible values for x is across the range in the sample space, okay? All right, sorry. There's a mix-up. I'm gonna fix this in the slides. For discrete random variables, of course, this must be the probability mass function, and for continuous random variables, this is the probability density function. Okay, so essentially this label and this label are mixed up. That is my bad. The important thing to remember is that discrete random variables, probability mass function; continuous random variables, probability density function. Why do we have this difference? The difference is that for discrete random variables, right? Remember, there are discrete events like rolling a die, that could be 1 through any number between 1 and 6 if it's a regular die. So we can directly kind of describe the probability of each of those discrete events because we have kind of a limited set of events, right? So we can directly describe the probability of x taking each and every one of those individual events, right? And that's why we have a probability mass function where we plug in a value of x. For example, we roll a 5, and we can directly compute the probability of that event, right? With continuous random variables, and I'm really sorry that this is mixed up here, this should be discrete and this should be continuous. For continuous random variables, so up here, of course, we have an uncountably infinite number of events, right? So the number of, for example, think about a distribution over waiting times when you're sitting at a bus stop, right? There's basically an infinite number of possible outcomes with regard to the exact time of when you arrive, right? Down to the millisecond or whatever, right? So that means that ultimately you can't really directly compute the probability of one individual event as like one specific millisecond time of when the bus arrives, because there are an unlimited or an infinite number of events. Each individual event kind of theoretically has a probability of 0, right? So all you can do is look at the probability of ranges of these continuous random variables to occur. So for example, the bus arriving between 9:50 and 9:51 or something like that, right? So due to this difference, we don't have a direct probability mass function that tells us the probability for one specific event, but we have a probability density function where for an individual value it doesn't give us a probability, but it gives us a density. Okay, and we'll look at examples later on where you see this difference between discrete random variables and continuous random variables. Okay. The next distribution that we can use to characterize these probability distributions is the cumulative distribution function. And the question this cumulative distribution function answers is, what is the probability that a random variable x takes a value equal or less than x, right? So basically this is now this is at least here it's now mixed up. For discrete random variables, this is denoted as capital F of x, or the probability of x being smaller or equal to x, and this is just the sum of all the probability mass functions for k being smaller or equal to x, right? So putting this into words, you could think of this as the probability of rolling at least a 5, rather than just rolling a 5 on a die, rolling at least a 5. And of course that's the probability of, or that's the sum of the probabilities of rolling a 1, a 2, a 3, a 4, and a 5, right? So that's what is described in the cumulative density function for basically any value of x between, for a die, 1 and 6. For continuous random variables, the same logic applies for the probability density function. The only difference is here that we can't again sum up individual probabilities because there are an infinite number of possible events. And what we have to do here, of course, is to compute the integral over the probability density function for the range of k being smaller or equal to x. So basically what we're doing is we're computing the area under the probability density function up to the point where small x, to compute the probability that x is smaller or equal than x. Okay. There are two more kind of important characteristics or important attributes to characterize probability distributions. The first one is the expectation, and we mentioned the expectation before. The expectation is just the expected value of a random variable, right? And it's denoted as the E of x, so expectation of x. If x is discrete, then the expectation of x is just the sum over the product of x times f of x, so x times the probability of x occurring, right? So for example, when we have a fair die, the expectation of x, the probability of each of those events 1 through 6 is the same, so the expected value is just the average, so that's 3.5, right? If our die is not fair, and for example the probability of rolling a 6 is much higher, then in order to compute the expected value, you have to take the product of the probability of each of those individual events times the specific value, right? If the probability for 6 was, a half rather than 1/6, that would be 1/2 times 6, and then, the remaining probabilities, whatever they might be, to compute the expected value, right? For continuous random variables, again, this is a little bit more complicated in the sense that we don't have individual discrete events with individual discrete probabilities. So what we have to do is we have to take, but the same logic applies in the sense that we take the product of the individual values of x times the density, so f of x, but again we take the integral with respect to x of that product, x times f of x, right, over the entire range of possible x outcomes, and that gives us then the expectation of that random variable, right? So I already mentioned the example of rolling a die. Of course, the probabilities of each individual side is 1/6, so it's a fair die. So that would be 3.5, the expected value. And the important thing is that this population, or this expected value, is different from the sample mean or the sample average, right? So for example, a sample mean of three throws could be, for example, 3 if we roll a 1, a 5, and a 3, and of course there is a deviation. There can be a deviation between the sample mean and kind of the expected value of the random variable, which we could also think of in the context of survey sampling as the population average that we're actually trying to make inferences about, right? So when we're talking about kind of uncertainty around our estimates, it's always the kind of the deviation between the sample mean and the true kind of population average that is ultimately unobserved. Okay. There are a couple of important properties of the expectation. One thing to keep in mind is that the expectation is a linear operator, And as a linear operator, it has a couple of important properties. So first, the expectation of a constant is just equal to the constant. If we multiply a random variable by a constant, then that is equal to the constant times the expectation. So we can pull out the constant in front of the expectation. Same with the sum. We can pull out, if we add a constant, we can pull this out as well. If we have the sum of two random variables, x and y, that are each multiplied by a constant, we can basically pull the expectations apart, expectation of x and expectation of y, and we can multiply each of these by a constant. And then in addition, if x and y are independent, then the expectation of the product of x and y is equal to the product of the expectations, right? But this only holds when x and y are independent. If they're not independent, then this we have to take into account basically the covariance between x and y, but we'll get to that at some point, right? So in the general case, it is not true that the product of x and y, the expectation of the product of x and y, is equal to the product of the expectations. Okay. The last important characteristics to characteristic of probability distribution that we also mentioned before are variance and standard deviation. And we already mentioned that at least when looking at sample standard deviations, they are of course equal to the square root of the sample variance, right? And of course the same applies here, but now we're looking at the variance and standard deviation in the population. And the variance of a random variable x is defined as the expectation of the deviation between x and the expectation of x. So that's x minus expectation of x squared, and we take the expectation of that, right? So that's basically the average square deviation from the mean, right? That's all that this equation or this expression ultimately shows. We can multiply out this squared term, and then what we're getting is the expectation of x squared minus 2x expectation of x plus expectation of x squared. And we can simplify this a little bit further. We can kind of as we just learned from the expectation rules, we can kind of separate out these sums. So we have the expectation of x squared minus 2 times the expectation of x plus the expectation of x squared, and so we can then combine these two terms, and what we're left with is the expectation of x squared minus the square of the expectation. So that's the definition of our population variance, either expressed like this or simplified if we multiply this out as expectation of x squared minus the square of the expectation. And of course, just like with the sample standard deviation that we talked about in the past, the population standard deviation is the square root of the population variance. There are a couple of important properties, again, of the variance, kind of similar to the expectation. The variance of a constant is equal to 0 because, of course, it's a constant. If we have the variance of a random variable x times a constant, and we want to pull out the constant, this is a squared times the variance of x, which you can basically just plug in here in the definition and use the rules for the expectation, and you'll see how you get to a square variance of x. And then we have the variance of a random variable x plus a constant. Adding this constant doesn't change the variance, so that's still the variance of x. And if we have, of course, that's kind of the combination of those two previous results, the variation of ax plus b is just a squared times the variation of x. And then lastly, if x and y are independent, then the variance of x plus y is just equal to the sum of the variances of x and y. And again, this does not hold if x and y are not independent, right? So for a lot of probability distributions, and in the next video I'm going to talk about different kind of, standard types of probability distributions for specific characteristic events, we can directly compute the variance and the standard deviation, the probability distribution, probability density function, or the cumulative density function, and already get an idea of kind of the shape of that probability distribution and work with those, right? But oftentimes it's quite difficult to derive exact analytical solutions for complex probability distributions, right? Not every probability distribution kind of follows these nice forms that we know or that we have encountered before. In these cases, we can often produce, and this is also discussed in the book chapter, so make sure to check that out if you haven't already. We can produce approximate solutions using the Monte Carlo simulation method. And that the Monte Carlo simulation method basically refers to a general class of simulation or stochastic methods that is used to approximately solve analytical problems by randomly generating quantities of interest, right? So rather than analytically computing the expectation or analytically computing the variance, we just take kind of random draws, we simulate random values from that probability distribution, and then approximate the mean or approximate the variance or other characteristics of that probability distribution just by looking at our simulated values and averaging over them or taking the variance of them and so on, right? Yeah, I think we'll leave it at that. We'll get to Monte Carlo methods later on, not in this week, but probably in the next week again. But it's already discussed in the book chapter as well, so make sure to kind of keep that in mind. Of course, there are deviations between your Monte Carlo simulation and that approximation and the analytical solution, and that is oftentimes kind of referred to as the Monte Carlo error. The important thing to keep in mind, though, is that we can kind of minimize that error by just increasing the number of iterations in our simulation, right? So the more kind of values we simulate, the smaller the deviation between or the random deviation between the simulation and our analytical solution is. Okay, so I'll leave it at that. I will, in the next part, talk about a couple of different broad classes of probability distributions for specific random variables.